We present VoMP. VoMP takes in a 3D geometry and, unlike prior art, it estimates physically plausible, volumetric, and fine-grained mechanical property fields that are fields of Young's modulus, Poisson's ratio, and density. These fields can be used in a physics simulator to produce accurate realistic 4D worlds. We propose VoMP, the first feed-forward model trained to estimate simulation-ready mechanical property fields within the volume of 3D objects across representations. So, now if you captured a Gaussian splat like this grape, you can run it through VoMP and in a couple seconds get the volumetric's physics property fields. This allows us to create physically realistic 4D world very quickly and without handcrafting. And yes, we can now drop a bunch of grapes on top of each other or do anything else with them. We compare VoMP against popular baselines and find VoMP to outperform these baselines. Like in the stool, the slice plane through the stool shows us that our method predicts correct properties for the internals of the stool. In the case of the shelf, VoMP is accurately able to identify the thin structures and give them accurate properties. For the couch, VoMP is able to accurately estimate the internal structure. And it works on meshes, SDFs, Radiance fields, Gaussian splats, and more. In general, our method can handle any geometry that can be voxelized and rendered out of the box. VoMP assigns volumetric properties, and thus this bed is given plausible properties of a cushion inside the bed. VoMP does not give the inside of the bed noisy properties. VoMP finds that the space inside the pot should be made up of properties that fall in the range of dirt even though the inside of the pot was not observed through external renders. VoMP can tolerate some noise in assets such as the Gaussian splat of a bowl with fruits segmented from a larger Gaussian splat. VoMP can accurately predict thin segments and thin boundaries like for the seat of the chair. VoMP can handle complex assets and complex materials like trees and accurately handle fine details such as understanding where all the leaves lie and gives them different material properties than wood. VoMP can handle complex volumetric materials such as annotating the properties of wood under the flowers. VoMP can handle thin materials and identifies the veins of the leaves. We show 65 Gaussian splat ficuses in a mesh container. Each of these ficuses is a Gaussian splat with the mechanical property fields estimated by VoMP. The container is a rigid mesh. We put estimated properties in a simulator to make this simulation of a Gaussian splat dozer running through a forest of 100 Gaussian splat ficuses. We show 18 Gaussian splats of small dogs falling through a rigid pachinko mesh. These simulations are run with the mechanical property fields estimated by VoMP. For this squishy dog toy, VoMP predicts a different property for the eyes of the dog. We show 3 oranges falling to the ground and an armchair falling to the ground simulated with a FEM simulator. These simulations look very realistic due to the high-quality material fields estimated by VoMP. We show a bowling ball falling on top of an armchair and a bed, simulated with a FEM simulator. Again, the material fields estimated by VoMP make the simulations look very realistic. We compare our FEM simulations with other baseline methods. We find that for objects like chairs or beds, models often are unable to assign valid materials, leading to the object collapsing under gravity when simulated. Furthermore, some baselines like Pixie often produce properties which allow for more deformation, leading to weird motions. Phys4D works well in some cases but fails when handling objects with more detail. One of the components of VoMP is the mat VAE. This latent space of materials allows us to do many interesting things like take a given material denoted by the middle bunny and then we can move across the 2D latent space of mat VAE to produce smoothly varying valid materials. The colors on the ground in each of these grids represent the displacement of the bunny vertices or the deformation of the bunny mesh, with yellow being more displacement and violet being less displacement. This shows us that we can produce smoothly varying simulations. MatVE allows us to take two materials like the materials on left and right here. We can now interpolate in the latent space of MatVE to produce valid materials. While naive interpolation might not produce valid materials, MatVE produces valid properties, that is, properties that map to a real observed material. Check out our paper for more details.